Okay. How about?
All right, let's begin. So it's a real pleasure to have one of our own, Professor Kevin Liu, give this talk in both the ECE department seminar series as well as our AI Edge AI Institute seminar series. As many of you already know, Kevin, he is an assistant professor in electrical and computer engineering, soon to be promoted to associate professor. He's our young superstar who works on a variety of different problems in machine learning and network optimization. Kevin has received a large number of awards from very, very prestigious conferences. And we are delighted to have Kevin present his thoughts and his work on federated multi-objective learning. So with that, I hand off to you, Kevin.
Yeah, thanks, Ness, for the kind introduction. I really appreciate it. So good afternoon, everyone. As you can see today, my talk title is Federated Multi-Objective Learning. So you can see from the title, the talk is basically about federated learning. And since this is a joint seminar, I guess many people in the online are working on federated learning extensively. But just for the general audience in the department, I'm gonna give a very quick introduction on federated learning. Just hope that everyone will be up to speed. So to understand what federated learning is doing, I think it's basically the best way is to kind of revisit the very basic machine learning problem, right? So as we know, but most of the machine learning training problems, we are just trying to solve this kind of expected loss minimization. Yeah, just like a machine learning 101 here. So the goal here is trying to minimize some loss function defined by both the model parameter X, and also this C is the training sample. Right? We want to find a model X such that we can minimize the expected loss given us some data set. Right? Now, of course, the workhorse algorithm is also very simple. Basically, this is our old friend stochastic gradient descent, right? We basically update the model parameter X iteratively, following some stochastic gradient, right? Defined by, again, the model parameter and the data sample. Of course, you can also do a little batching, right? So you can do a mini batch BK here. And the SK is your step size or learning rate. Okay? But basically, all the distributed machine learning and federated learning start from here. And this is because this summation can be decomposed, right? Decomposed, and the workload can be distributed into different workers or clients. And then, you can start to enjoy the benefit of parallelism, and then the whole training process can be significantly accelerated. And that's the basic idea. Now, of course, right? We know that basically the huge success of machine learning in perhaps the last decade is largely due to this kind of adoption of like a large scale distributed learning parallelism. Like basically, people have built data centers, supercomputers to train very sophisticated models. On the other hand, the same idea is also used in federated learning. Federated learning is mostly or more popularly deployed in the edge. Right? So now let's take a look at the structure. Okay, so this is a pretty typical structure of federated learning. You have a parameter server and a bunch of clients, and you can also think of these devices as workers, right? Now, a different feature compared to the traditional distributed learning is that the data set is privately owned by each client, so there's no shared, global data set. So basically, the interaction between the client and server is the following. So the client will take some sample locally, and then compute some kind of stochastic gradient or some update, right? So this gradient here is kind of loosely defined. You can also think of it as just some model update based on the local data. And then the client will send the update to the server, and the server will aggregate everyone's input and then do some aggregation or averaging, and then broadcast the new model back to the client. And then this process will keep going, so on and so forth, until some sort of convergence will be reached. Right? So just to give you guys a little historical perspective, federated learning was first, the terminology was first invented in 2016, even though the official paper was published in 2017. But in fact, one of my colleagues, he claimed that he invented federated learning even much earlier, back in 2012, something like that. But he never used this terminology. So he was kind of a little grumpy because he didn't get the credit. But anyway, so the key motivation of FL is that we are trying to deploy this kind of learning framework on mobile and edge networks. Right? So basically, all these edge devices would be something like a smartphone, tablet, or laptop computers, or some sort of like a less powerful devices, okay, compared to those in the data center. But a nice feature about federated learning is that there's no need to collect the data to the central server locations, and therefore, in some sense, FL provides a little better data privacy. Okay, but of course, how to guarantee privacy is also a huge topic in FL. Merely using this kind of architecture still cannot, or still not sufficient to guarantee privacy in a rigorous sense. Okay. Now, there are lots of challenges in federated learning. So these are some of the more typical challenges you will see, including the data set could be unbalanced. The data set distribution could be non-ID across clients. And the number of devices could be huge. So later you can see in the cross-device setting, we are talking about tens of thousands of devices. And there could be also limited communication bandwidth between the server and the clients. And some clients may or may not be available from time to time. Right? So all these are basic challenges in FL. Now, as I just mentioned, in FL, there are two popular settings in the literature. One is called cross-device, and the other one is called cross-silo. Okay, so basically, cross-device setting will have a huge number of unreliable clients. Now, in comparison, the cross-silo setting will have relatively fewer number of clients, but these are more reliable, more powerful clients, like a hospital, banks, something like that. Okay? So this is this chart also compares cross-device FL and cross-silo FL with the traditional distributed learning. Right? Now you can see basically in the traditional learning, things are pretty ideal, very nice. You have ID data set, you have fast wire communication, everything is centrally orchestrated, all things like that. But in FL, for this cross-device FL, data set would be non-ID. And you have slow wireless communications, the data set, number of devices is huge, right? Things like that. So these are the nice, probably the ugly features compared to distributed learning. Right? But on top of that, two major challenges arise from FL are these two. Okay, one is the data heterogeneity, and the other one is the system heterogeneity. All right, so FL has been very popular, largely due to these kind of well-known applications popularized by big tech companies like Google and Apple. Right. So, for example, one quintessential example in FL is this Google Gboard, which is your smart keyboard that you use every day. So you can think of it as that on your phone there is actually a small language model. Right, that takes your everyday's typing as input and then leverages all these data to train a model that could predict your next input, something like that. Okay? So this is a very popular application. Now, Apple also has the similar counterpart, and it turns out that this Hey Siri also leveraged FL to do something. Okay? Now, on the enterprise side, people have also using these kind of FL idea to do financial risk prediction, reinsurance, pharmaceutical discovery, all things like that. Now, in fact, if you look at the last few years top conference in ML, you will consistently see that FL has been one of the top 10 topics almost every year. Right? So you might wonder why there are so many interests, such a passion about FL. So in terms of research, FL is internally interdisciplinary. So now, of course, FL is a branch of machine learning, right? But Mila, it also involves lots of different areas like cryptography, security, privacy, fairness, compressed sensing, so on and so forth, right? And also networking, which is actually my own traditional area. Okay? Now, and it turns out that many of the hardest problems in FL are sitting at the intersection, across these multiple areas. Now, if you look at the basic process of FL, okay, so these are the basic elements. Basically, all FL algorithms will involve some sort of a client selection, how to do the broadcast, how to kind of design the client-side computation, and then how do you do aggregation and how you do model updates, right? So basically, every tweaks, every difference in all these components would lead to some kind of FL algorithms. Okay. Now, but out of all these algorithms, turns out this algorithm called Fed average. Some people call it local SGD or parallel SGD. So this is actually the basic template. You can think of this as the basic template of all the FL algorithms. Okay. So the idea is the following. Now let's say you have, for simplicity, we assume that we have a fixed number of clients n, and each client will, later on there's a parameter called m. So each client will perform some local update up to m rounds, m updates per round. Okay. So T is the total number of communication rounds between the server and the client. Now, so essentially, initially the server will kind of initialize some model parameter x0, and then the server will run, up to T rounds. Okay, and then in each round, basically, the server will select a subset of clients. So this set could be a random set, okay, or it could be all the clients. And then for each client in this selected set, they will do something in parallel. Now you jump to this client-side client-side routine. Okay, so in here, the client will take the the model up from the server as the initial point, and then the client will do k up to k local updates. Okay, so in the most basic Fed average, this update is just is done in an SGD style. Okay, it's very simple. And then after k steps, the client will return the result back to the server. Okay. Now at the server, everything will be averaged, and then this updated parameter will be broadcast to all clients, and then that's the whole process. Okay. Now, of course, there are many different ways to do it. When you send this xk, you instead of sending xk directly, you can also send the difference between two iterations. Okay, so that may actually help improve the communication efficiency, because when the process is getting close to convergence, this xk is becoming smaller, okay? And then the number of bits to be transmitted will be smaller. But of course, and when you do that, you need the system to be stable, right? There are all kinds of trade-off involved, and if you tweak this SGD update a little bit, or if you change the averaging step a little bit, all of a sudden you get a new FL algorithm. Okay. All right, so that's the basic of FL. All right, so now let me get to our main topic today, which is federated multi-objective learning. Okay. So this is actually based on our very recent work, just published in NeurIPS, in the last December, okay, a couple weeks ago, actually. Okay. So so this is a joint work between my student, Haibo. Haibo is the lead author of this paper, and he's now actually a tenure-track assistant professor at the Rochester Institute of Technology. Okay, so he's my first academic descendant. And this is actually his very last work at OSU. Another main contributor is Zhu Qing. So she is my fifth-year PhD student right now, and she's actually on the job market this year. So, you know, for all the people online from outside of OSU, you may consider her if you have a position. Okay. So, and also this work is in collaboration with two great friends and colleagues from Amazon, Chaosheng and Michi. So many of the multi-object discussions started from my collaboration with these two guys. All right. So now let's talk a little bit and motivate a little bit why we care about multi-objective optimization. So multi-objective optimization actually arrives from many applications. So remember that I just mentioned two Amazon colleagues. Okay. So in fact, many of this MO problems arise from this recommended system design at Amazon. Okay. So for example, if you do a shopping, right? Now, as this designer of this recommended system at Amazon, they will have to consider, you know, different customers. So some customers prefer cheap products. Okay? Some customers prefer, you know, brand names. Some customers prefer fast delivery speed. Right? So basically, every customer has different objectives. So I really want to design a recommended system that can take care of such a diverse set of objectives. Right? Now, another application of MO is this kind of so-called pre-training, fine-tuning pipeline that is recently becoming very popular in all these kind of foundational models, right? like GPT and ChatGPT, right? So basically, ChatGPT is just a chatbot built upon the foundation language model, GPT-3 or GPT-4, right? So now, when you have a foundation model, basically you have a model that has taken a lot of knowledge and do the pre-training and learn some good representation, right? And then after that, you need to do a lot of fine-tuning so that you can adapt the foundation model to many different tasks. So naturally, you have a multitask problem here, and then you have multiple objectives that you need to worry about. Now, turns out federated learning itself is also
Okay. So typically, when you do multi-objective optimization, you always have a Pareto from.
Yeah, I'll get to that. I'll definitely get to that. Great question. So turns out federated learning itself is also multi-objective, right? So if you know a little bit about FL, there are a lot of people doing or working on the so-called personalized FL. So here, naturally, you want to, you know, train some local model based on some, the global model, right? And then eventually, you want to develop something that can also cater to the local data set. So in that sense, there's also a multi-objective optimization in here. And last, this example is called contrastive learning, right? This is also another one, kind of a very popular unsupervised learning technology. So basically, all the data are unlabeled, right? So how do you want to train a model to tell the difference between a cat and a dog or something like that? So you will augment the existing data set, right? Create so for example, like a black and white image for the dog, and then this is another image of a bird, right? And then of course here I want to construct different objectives such that, you know, the loss that measure this augmented data and your urgent data will be small, right? And then the loss between these two completely different animals would be huge. And so you want to train a model like that. So naturally, you also see some multi-objective optimization. Right? So the list can go on, and so yeah, there's a lot of such application. All right. So now mathematically, if you look at MOO, this is basically the setup. MOO is nothing but a kind of multi-task learning or multi-objective, multi-task learning. But compared to other types of multi-task learning, here the structure is a bit different. So we want to minimize or optimize all these objectives simultaneously. Now, if you want to optimize these objectives sequentially, that will lead to another very interesting area called continual learning and things like that, right? But here we want to do it simultaneously. Okay, so now basically you are working with a vector value objective function instead of a scalar value. Right? And then the goal is trying to find a model parameter x such that, you know, you minimize this objective in some sense. Later I will get to that. All right, so now just a very quick overview of all the objective functions. I'm sorry, all the MOO methods. So roughly speaking, you can classify all these methods into gradient-free and gradient-based methods. So these gradient-free methods are relatively older ideas. So right now, at least in the machine learning community, these are not that popular. So I'm not going to say too much about these things. So I'm going to focus a bit more on the gradient-based methods. Okay. So here, turns out that this method called multi-gradient descent algorithm, or MGDA for short, has been quite popular, and actually has been.
Just FYI,
Uh,
gradient descent methods are older than gradient
Of course.
methods. And then I guess there is a resurgence in gradient-based methods.
Yeah,
It's a different story.
Right. Yeah, of course, everyone knows gradient descent. It's nothing new, but somehow this MGDA idea, in fact, you can see that the earliest,
Yeah.
at least as far as I know, the earliest version came out in the 80s, and people had been rediscovering the same idea, you know, and the same, like a reincarnation of this method has been, you know, coming up again and again. But lately, you know, due to all these kind of recent application of ML, so MGDA and the stochastic version of MGDA receive more and more attention. However, if you look at all these multi-objective optimization methods, you'll notice that most of these methods so far are centralized. Okay, and basically that means that all the training data are aggregated to a centralized location. Now, that basically is in contradiction to many of the multi-objective optimization problems that are coming from multi-agent nature. Okay, so basically this centralized MO does not satisfy many the application multi-agent setting, which actually motivates this MO study in the first place. Okay? So in this work, we try to kind of extend the current MO methods to these kind of multi-agent, multitask setting. Okay. However, if you look at how to extend this, it's actually not that clear how we should do that. Okay? So of course, if you want to do federated multi-objective optimization, these old challenges are still there, the data and system heterogeneity. But there's another heterogeneity that may come into place, right? Which is this objective heterogeneity, meaning that different clients may have a different set of objectives. Okay? Now, because of that, it's not even clear how we should define a federated multi-objective optimization. Okay, so basically, in order to extend MOO to multi-agent setting, we need to be able to kind of define some new, clear problem first. Okay? So now, because of that, we want to answer the following fundamental questions. So first of all, what should a general federated multi-objective learning framework look like? Okay, so this we have to resolve this in the first place. Now, after we defined a good problem, then we will also need to consider, under all these kind of objective data system heterogeneity, is it possible to design some FMOL, basically federated multi-object learning algorithms, with some sort of Pareto stationarity guarantee? Okay, I'll get to this definition in a few minutes. Now, all right, there's another question. So if we can answer question 1 with a yes, then can we characterize the convergence speed, right? So if we can guarantee convergence, then another question is how fast the conversion is. Right? So basically, we are these are the questions that we are interested. Now, in here, basically, we start from defining the first federated multi-objective learning framework. Okay? So now this is a synopsis of this work. As I said, we defined the first general FMOL framework that allows different clients to have different objectives. Okay, and we based on this, we can support a wide range of application. And in fact, many of the existing multi-agent and multi multitask learning can be considered as a special case of this general framework. Now, based on this framework, we further propose these two algorithms. One is called MGDA. This is a federated version of MGDA, and this FSMGDA is the stochastic version of FMGDA. Okay. Now, both of these algorithms can be considered as the MOO extension of Fed average in the basic FL to this multi-objective setting. And also we show that they achieve the same convergence rate as the single objective counterpart. All right, so now let me be a bit more clear, a bit more specific. So before we dive into all the technical results, we have to basically set our language straight. Okay, so kind of define the several basic notions in MOO. So as Shanker just mentioned, when you talk about MOO, inevitably you get to some Pareto front, right? So in Pareto front, basically, you first need this kind of a basic concept called dominance. Okay, so here we let's say we have 2 points X and Y, and we say X dominates Y, if and only if for every objective Fs, okay, this Fs of X will be less than or equal to Fs of Y for all objectives. And furthermore, there should exist at least one objective where Fs of X will be strictly less than Fs of Y, right? So these are pretty intuitive, right? Now, based on this notion, this dominance notion, we can further define the so-called Pareto optimality, right? Then we call a solution X star to be Pareto optimal if it is not dominated by any other solution, right? So that's the Pareto optimality. And then this Pareto optimality could be too strong. So sometimes we will also like to work with a slightly weaker optimality. So we say a solution X star is weakly optimal, weakly Pareto optimal if there's no X such that this relationship holds for every object function. Okay, so that means that if there's another X where equality holds, that's fine. Okay, so we allow we allow tie. Okay, in some sense. All right. So lastly, we need this notion called Pareto stationarity. So that's because in many cases, in many problems, if the object function of the problem, of the underlying MOO problems are non-convex, then basically it's hopeless to find a MOO, a Pareto optimal solution, right? So even for a single objective, it's already NP hard, right? So for MOO, we have to, sacrifice a little bit and be willing to work with a little weaker performance metric. Okay, so it turns out in MOO, the performance metric is this Pareto stationarity. So essentially, we say that solution X is Pareto stationary if there's no common descent solution. Okay, so basically, we cannot find a D such that this D will form a tube angle with respect to every gradient. Right? So, or in other sense, if all the gradients form a cone, right, then this common descent direction should be pointing to in the opposite direction outside of that cone. Right? So that's a geometric interpretation. All right. So with all these, now let's get to another basic element. This basic MGDA method, right? Multi-gradient descent. All right. So yeah, as I just mentioned, this idea has been. It's actually not very new, but it just has been rediscovered, over the years, and every time there's small new elements into it, and new theoretical insight, new convergence rate analysis, something like that. Okay, but the basic idea is still pretty much the same. Now here, now if you have a multi-object optimization problem, then the first step you do in MGDA is that you will find some optimal weight, lambda star, okay, of this collection of gradient at some point X. by solving this sub-optimization problem. Okay, so basically you look at the linear combination of all these gradients, and then you minimize the norm of this gradient, right? So and then and then the arc mean of this is basically your lambda. Okay. Now you might wonder why we need to do that. In fact, this is actually coming straight from this so-called this stationarity, okay, the Pareto stationarity. So if you try to minimize the maximum Pareto stationarity of all these objective function, then it turns out the dual problem of that stationarity minimization is exactly this problem. Okay, and then basically, by solving this problem, you get the minimum of the max Pareto stationarity gap. Okay. All right. So after you get this lambda, then this common direction is basically this. Okay, the negative of this lambda combination of all the objective gradients, and then you just perform this kind of very simple update. Okay, so you update x by following this common descent direction, and then you go back to step one and you do this repeatedly. All right. So any questions at this point? All right. Okay, so now that's the basic the basic MGDA. Now let's get back to FMOL, okay, FMOO, or you can say. So now, as I said earlier, we need to define a general framework, right? But in general, it's not very clear. You have multiple clients and you have multiple objectives, right? How should we define this problem in a systematic way? Okay, so it turns out we can do the following. Now here we assume that the multi-object system has m clients, okay, and then each client may have up to s objectives. Okay? So basically here I define this F matrix, which collects the group of this F basically collects all potential objective function. Okay? So some of these functions may or may not be here. So basically here these rows are the type of some interest or some objective at each particular client. Okay, and each column is basically representing a client. Now, some client may or may not care some of the objectives. Right? So how to represent that? So you can basically define this A matrix. Okay, this A matrix is a binary objective indicator matrix, where some element ASI is equal to 1 if this task S is of client I's interest. Okay, otherwise this A will be 0. Okay, so basically by using these two, we can define this multi-objective optimization problem. Okay, and then accordingly, we also for each task or each objective S, right? We basically collect this define this global objective function fs of x as this average of all these local objectives, right, of all the relevant clients. So basically, you can see I define this RS as the the clients that are relevant to some objective S, right? And then using this set, I will just do an average, and that's my S one of the objectives of fs of x. All right, so that's the general framework. Right? So you might wonder what's so interesting here. So it turns out this is a general framework in the sense that if you pick these S and A in a certain way, then you can actually recover many different types of multi-learning problems. Right? So for example, if you choose this A to be an identity matrix and let this S to be just M, okay, the number of objectives is the same as the number of clients, then basically this problem will correspond to the standard multitask learning or personalized federated learning. Okay? Now, on the other hand, if all clients share the same set as objectives, right, meaning that if this A matrix is all 1, then basically the entire problem will become solving an MOO problem collaboratively with the decentralized data. Okay? So in some sense, you can also think of it as every clients work together to optimize the same set of objectives, right? Such as optimizing fairness, privacy, accuracy, or something like that. All right. Now, of course, the most general case is that every client has a different may have a different subset of objectives, right? So the objectives are heterogeneous. Then, basically, this framework will allow each client will have a distinct preference. Okay? So this would be the most general case. All right. So that's the general framework we come up with. Now, based on this framework, we were able to come up with this corresponding federated multi-gradient descent method. Okay, so the method looks like the following. Okay, so now in each round, each client T, okay, now each client would basically get synchronize this local model with the server, right? For each objective S. And then we will perform a local update very similar to standard Fed average. Now, of course, if you have if you want to work with full gradient, then you follow this FMGDA version or option. If you want to work with the stochastic gradient, then you follow this stochastic version. Okay? But essentially, they are very similar. Here you perform K up to K local updates at each client. Right? This is in the exactly the same spirit as the standard Fed average. Right. So here in this very basic version, we just simply take either gradient of stochastic gradient. Now here I highlight these two two numbers, right? So this is actually the so-called local learning rate. Okay? Later on, you see another learning rate called global learning rate. But I'll get to that later. But basically, these are the learning rate at the local site. Okay? Now, after after K steps, then you will have some accumulated update, right? It's exactly the same as Fed average. And then depending on either it's deterministic or stochastic, you feed back the accumulated update back to the server. And then at the server in round T, right? Then the server will do the following. For each objective, you calculate the average for all the relevant clients, right? You calculate the average accumulated update for this relevant set, and then based on this, we will solve based on this accumulated update. We will solve this optimization problem, subproblem, in a very similar spirit as the single agent MOO, right? But now you just replace those gradient by this accumulate update, right? And then after that, you figure out the common descent direction, follow this direction to do one step, kind of like a gradient update, right? But here, you can see there's not a learning rate. So this learning rate, the two-sided learning rate idea has been used in some of our previous work. So the idea is basically try to allow the server and the client to follow a different schedule so that we can kind of mitigate a very infamous problem in FL called client drift. Okay? So if you set this eta to be 1, you will recover the standard Fed average. But if you allow this to be distinct, then you can actually tweak these local and global learning rate in an intelligent way so that you can mitigate the client drift effect. Okay. All right, so now that's the basic algorithm. How much time do I have? 2. Okay. So yeah, so now let's get to more heavy stuff. So now let's first look at the convergence rate result of this the basic federated MGDA. Now, basically, under these standard assumptions, right? If you work in this area, you immediately know that these are very standard assumptions, like Lipschitz smoothness, bounded gradient, right? But of course, here now you need this for every objective. Now, after that, basically, if you pick these global and this is a global learning rate to be a constant bounded by this, then the sequence produced by FMGD will satisfy this complicated convergence rate error bound. Okay, convergence error bound. But here I want to highlight this is that this is like a vanishing term with respect to t. Right, as t gets large, this one should be small. Plus a constant here. The constant depends on various system constant, right? This case, the number of local updates, the larger, right? Then you have a larger delta. And basically that captures the more severe so-called client drift. If the function is not that smooth, right? You have big L, then this one is also big. And yeah. And also S is the number of objective, right? The more objective, this constant can also be become worse as well. But the nice thing here is that you can see that this delta depends on this eta L. This is the local learning rate we can control, right? Now, by cleverly controlling the local learning rate as the following, okay? If I know the T, then I set this learning rate T accordingly. Then actually we can show that this result directly implies this so-called this Pareto stationary convergence rate, which is 1/T, right? So yeah, if you are familiar with gradient descent, you know that this convergence rate is exactly the same as standard gradient descent. So in some sense, we're kind of recovering the standard result in the single agent counterpart. All right, now if the algorithm is not, if the problem is strongly convex for each objective, right, then we can say a little bit more about FMGDA as well. So again, here under all these standard assumptions, plus this mu strongly convex assumption for each objective, then we can show that as long as you pick these, global learning rate nicely in the following sense, and also this is also a pretty interesting idea. And then here, if you stop the algorithm stochastically with this probability, okay, so you can think of it as you have a random clock. You will run the algorithm up to T's step, but you also have a random clock that can prematurely stop this algorithm with this probability each time T. Okay, then we can show that this is the again the convergence metric. So here I don't want to get into too much detail about this convergence metric, but this is actually the corresponding convergence metric in a strongly convex setting where we can actually directly measure the optimality gap rather than just the stationarity gap. Okay, so you can show that some kind of the optimality gap is bounded by this term plus some kind of garbage in here, right? And then so now based on this result, similarly, if we set this eta L to be in this order, then we can actually recover this pretty efficient Pareto stationary convergence rate. Okay, so yeah, it's of that order. It's actually a linear convergence in this sense. Okay. Now let's talk about the stochastic version. Now, in fact, stochastic multi-objective optimization is still a relatively new area. Okay, so people still have a lot of different opinion in how to pick the assumption. So before us, there are some other people, taking some weird assumptions and things like that. So I don't want to get into too much details. But my point here is that even in this single agent MOO, okay, this assumption is still kind of up to debate right now. So here we propose this so-called alpha beta smoothness assumption, and you can think of this as like a generalized Lipschitz smoothness assumption compared to traditional optimization. Okay. Now, under this, and also these kind of unbiased stochastic gradient, bounded stochastic gradient standard result, and again, if you can pick the learning rate globally, with this global learning rate, right, then you have this bound for that common descent direction. Right. Now, it's pretty complicated. And then if you take these local learning rates to simplify the results a little bit, eventually you can recover this kind of 1/square root of T convergence rate for the stochastic version of FMGDA. Okay. So now, again, if you're familiar with SGD and or some related optimization topics, you will know that this is still the same convergence rate as the stochastic gradient methods, right? Now, lastly, for the stochastic version for strongly convex case, right? That's the last combination. Again, under all these standard assumptions, and then let's say you set this a random clock to terminate the algorithm with this kind of probability, right? Then you can show, again, this is the this new performance metric, right? Measuring the optimality gap under strongly convex setting. This bound is of that particular quantity. Right? And then again, let's say that we can set the learning rate locally in this kind of a T adaptive setting, right? Then we can eventually recover this kind of 1/T convergence rate under the strongly convex setting. Okay. Now again, you also realize or recognize that all these learning rates all these convergence rates are exactly the same as their counterparts in this single objective set. Okay. All right, so a little bit numerical result. So here, actually, we perform some, you can look at these simple multi-objectives problems, like we use these to kind of illustrate the impact of batch size, and batch size, yeah. So this, and also the number of local updates on their convergence behavior. Okay. So here we look at this kind of a multi MNIST data set, which is just a simple extension of the the original MNIST set. So here the task is the following: you have each client will have two images. One is on the left and one is on the right. Okay, so basically each client will need to classify what digit is on the left and what digit is on the right. Okay? So essentially you have a two task problem. So now you can see under different batches, right? So all our proposed this federated stochastic MGD will converge, right? Of course, as the batch gets larger and larger, we have better and better convergence. And now here, this is looking at the impact of the number of local updates on the training. Okay, so now as you can actually, pretty interestingly, as this K gets larger and larger, we actually have a better and better convergence. So we suspect that yes. So with all these local learning rate adjusted appropriately, and as this K gets larger and larger, we actually have a better, more accurate gradient, like a common descent direction compared to the cases with the smaller K. Okay? So this one is a little, surprising to us, but we guess this could be just due to some numerical-ish reasons. Okay. Now this is another slightly larger example. Basically, we have 8 tasks here. The problem is trying to predict the river flow at 8 different locations of the Mississippi River. So there's a standard data set called river data set. Now here, basically each task represents one location. Okay, so this is like a radar chart. We again measure or evaluate the impact of the local updates K on the overall algorithm performance. Now you can see as K gets larger and larger, we also have a better and better result. So basically, the more concentrated the footprint is, right, the better the performance. Again, this one look at batch size. Okay, so now you can see with a larger batch size, we have a better performance as well. Okay, so lastly, we have an even larger task, larger problem with 40 tasks. Okay, so we are using this so-called Celerber data set. So here, basically, we are doing some, facial attributes classification. So the data set is basically all these facial images with 40 attributes. Now, basically, based on all these attributes, we do some facial classification. And basically, this is a 40 task problem. And again, you can see, again, we measure the impact of batch size on the performance of the algorithm. Right? So this one is non-ID data, and that one is ID case. But in either case, you can see that the algorithm converges pretty nicely, and as the batch size gets larger and larger, the algorithm will be able to get good performance in all objectives.
So can I, stupid question, but isn't that the default case? The batch size gets larger, you expect good performance.
Yeah, of course.
Don't you want the other
Yeah,
way
yeah.
around?
But I'm just showing that they converge pretty nice. So that's the point of the result. Okay, so to conclude, basically in this work, we proposed the first general federated multi-object learning framework that extended this MO from single agent setting to federated multi-agent setting. Right? Now, basically this framework consider both objective and data heterogeneity. For now, we haven't looked at the system heterogeneity that much. But I think that should be done in a relatively straightforward fashion. We also proposed two algorithms. One is stochastic, one is deterministic, that will kind of enjoy some Pareto stationary convergence rate guarantee. Okay. Now, these are some of the future directions. We are also thinking about these problems right now. So these problems may include, how to develop acceleration. Right now, SGD or GD, right? These are standard results. We may be able to use momentum or variance reduction, or a combination of all these ideas to further accelerate federated multi-objective learning. We can also consider how to develop communication efficient scheme like compression, many other different ideas already in the federated learning literature to help reduce the communication cost. Okay. So with that, I will stop here, and thanks for coming. Any questions? And also people online, is there any question?
I have a question on probably one of the last slides, 32 or 31.
This one?
Yes, this one. So on the left two, there is basically objective 39 that is probably something's going on there that is not being minimized.
Yeah.
Probably. So is that may be caused by some outlier gradients from some clients? Say that you have 100 clients. One of them is looking to minimize the cost for vegetarian food. The other ones are all meat, right? So when you do the average of the gradients, then they're going to represent kind of the outlier, kind of will never be able to minimize it.
So, yeah, I'm also not very sure what's causing this kind of appearance. I also need to check with my students more carefully. But one reason is probably due to the data set. There could be something going on. The other one is I'm not exactly sure whether the scale are set consistently. So the scale of this objective could be pretty huge. So that may not imply a bad performance either.
Okay.
So I need to double check with that.
But could that happen that, since you just averaging all the gradients from all the clients, if you have one that is particularly different from the rest, so it's basically an outlier, is that client going to be able to actually get a good model over time?
So I think theoretically, as long as you have this kind of convergence rate or depending on whether it's convex or non-convex, right? So as long as you have some stationarity guarantee, then you would expect good performance. But of course, I would caution that all these problems are potentially non-convex, and so even achieving a Pareto stationary point may not imply good performance in the direction. So I wouldn't call it outlier. It's just the nature of the problem.
Yeah.
Where some of the objectives are just so difficult to optimize. Right? Yeah.
Thanks.
Have you guys looked at, there's a lot, oh, sorry.
This one. Which will chat. So yeah, there's a question in the chat. So Jia, can you just unmute yourself and talk? Yeah, it take less time for me. I need to read through it.
Hello, Professor Liu, can you hear me?
Yeah, go ahead.
Okay. I have two questions. So the first questions is about the bounded stochastic gradient.
Mhm.
We know that it is a strong assumption, since
Mhm.
like recent learning theory papers tend to relax this assumption and like make it even a weaker condition like bounded gradient variance,
Mhm.
or even like the weak growth of this stochastic gradient. So
Yeah.
how do you comment on this likely attack from the reviewer if you are like submitting your paper to the top tier conference?
Yeah, good question. So I agree. If in a single objective literature, if you assume bounded gradient, now the reviewer will be outrageous. These are considered very strict, or unless it's in earlier work. Right now, bounded gradient is usually considered not necessary. But in turns out in this multi-objective setting, we do, at least for now, we do need this. Whether this can be relaxed or not, I think it would be interesting to look at. I wouldn't say it's not, but at least based on our analysis right now, due to the complicated nature of MOO, we still need this bounded gradient to make the proof work. Okay? So in fact, I also yeah, this is also a personal open questions right now, whether we can relax this bounded stochastic gradient and also gradient, I think.
Thank you. So another question is about the strongly convex case. Yes, here you assume both the strongly convex and the bounded gradient. So I recall recently there's some paper, for example, the optimization method for large-scale machine learning published by Bottle in 2018. He pointed out that the bounded gradient often does not hold when the objective function f is strongly convex. So yeah, how do you comment on this aspect?
Yeah, I'm not very familiar with the paper you mentioned. I would argue, in most applications in reality, right? So we are not really dealing with infinity. Basically, the data is bounded, and also you will also say the computing device can only handle bounded precision, something like that, right? So I think in reality, I think it may not be a very crazy assumption. Theoretically, whether or not there's a conflict between bounded gradient and also strong convexity, right? You said.
Yeah.
I'm not so. I'm not so clear at this moment. It may be interesting to look into that. And maybe you can also send me that reference. I'll take a closer look.
Okay, I can send you like two papers. I think both.
Yeah, I really appreciate it.
Okay. Yeah, thank you, Professor Liu. I have no questions.
Thanks. Anything else?
So Kevin, I have a slightly different question. So in control system literature, there's been a lot of work on decentralized optimization. Have you guys looked at any of them? Very recent.
Yeah.
3 years.
You mean decentralized in the sense of having no server, right? Everything is
Everything
completely.
decentralized,
Yeah, we do. In fact, I would say my group has probably one of the largest serious work on decentralized optimization. So we have been working on lots of different decentralized optimization problems, including just simple single object, single objective, and also simple minimization. And then we also have decentralized min-max, decentralized bi-level, all that kind of stuff. Yeah, maybe decentralized MO can also be another topic to look into. Yeah, so all these decentralized methods are somewhat based on consensus. You don't have a server, right?
Yeah.
You do gossiping and
Yeah.
We do have a lot of work on that.
Okay, all right, I didn't know.
I can send you some of the
Okay.
if you're interested. Okay.
Okay, I have another question. This is born of pure ignorance. Right, ignorant. How do you compute the gradient?
How do we compute a gradient?
So when I do optimization, we explicitly avoid computing gradients. We always formulate an adjoint problem. Right, so when you do scientific computing and you do optimization in a scientific computing setting, you formulate an adjoint problem so that you avoid computing gradients.
Yeah, I think.
Because gradient computation is very expensive. It's
I'm not sure if
incredibly
this is
expensive
in
for-
different error or not. So now, of course, if the expression is tractable, there may be easy to actually calculate gradient in closed form, right? But if it's not, or the function is complicated, there are so many
You don't
tools.
have function, right? Your samples are. function.
Right. But there are so many different tools to do these things numerically. Yeah, so I'm pretty sure my students actually are more familiar with all these than me. So I believe that there are so many different tools to calculate gradient, at least numerically.
Not for scientific computing, but that's okay.
Yeah, that's not my expertise. I haven't
No, that's-
really.
I'm just asking, I'm just
Yeah,
thinking.
yeah.
How do you?
There
grade?
could be a lot of challenges in really computing a gradient accurately. But at this point, our focus is not there. If you just take the gradient as input and then start from there.
That's why I said, it's out of ignorance.
That's a good point. Yeah, I actually haven't thought about that, at least for now, so.
Somebody has another question. Michelle? Or is that one more? Is
Oh, yeah.
that the old one?
Yes, it's the old.
Okay.
Oh, it's already answered?
Yeah.
Okay.
How is the client selection going to affect the performance? Well, okay, so
Oh, yeah,
it probably depends on the local data.
So right now,
If
we
the
actually
local
have,
data being, let's say like the quality of the data
yeah, so
taken into consideration.
typically, right now, actually, we don't consider client selection in here. But it might be an interesting problem to look at, but usually people just assume uniform selection. Yeah, anything other than uniform would be creating some problems in conversion.
There's always so like those, I think in the first few slides you mentioned that like, if the client is basically it's a mobile
Yeah,
device and is
there are so
charging
many-
and is idle, you know.
Right.
But then what you want to really select is the client with the useful data.
Right, useful data and also whether or not the client will be available is not an issue. So, yeah, ideally, you would like to have a uniform distribution if you care more about the global objective. But if you want the system to be, more personalized or having some favor in some of the clients, I think, yeah, that's up to the designer how to do it. I don't think there's a right or wrong answer, honestly.
Because technically, if you can have more information on the local data, then you can kind of group clients and avoid the
Yeah.
multi.
There are tons of work, like
Multiple files.
doing clustering, doing clustering or even having different hierarchy. Yeah, I think, FL is definitely a huge topic, it cannot be simply covered in just one talk, yeah.
There was a paper a while ago, I don't remember what conference, but I said they were basically, it was more like system work.
Yeah.
Where they were doing federal learning while the device was active and the user was.
Right.
interacting with it, so there's.
Yeah, so, yeah, actually, Mike will also have some papers on whether or not, what happen if you have some clients that rarely participate.
Right.
Yeah, something like that, and then whether we can still guarantee some sort of generalization performance, without like a kind of uniform participation. Yeah, so yeah, that lots of open problems in here. All right, so if no other things, and just stop here. Thank you for me.